As the thermal motion of atoms in a substance approaches zero, the kinetic energy of the atoms approaches zero, and the temperature of the substance approaches a lower limit. This limit is absolute zero of temperature. Absolute zero is the temperature at which no more energy can be extracted from a substance, and no further lowering of its temperature is possible. And here are some temperatures. I have the full-blown one, but it's kind of tall, and it's hard to see things very clearly. So the bottom one at 0 Kelvin is just above that is helium boils, then oxygen boils, dry ice, ammonia boils, ice melts, etc. We're going to surface of the sun, plasma, surface of a star, and all the way up to a hydrogen bomb. Isn't that pleasant? So we can artificially induce a temperature here on Earth that exceeds parts of the sun. Looking for a diet plan? Burn more calories than you consume. This is the only diet plan firmly based on the first law of thermodynamics and guaranteed to work. It's not really suggesting that you diet, it's just trying to make a point. Then that is the first law of thermodynamics. Energy is neither created nor destroyed, it exists. The first law of thermodynamics is the law of conservation of energy applied to thermal systems. The first law of thermodynamics states that whenever heat is added to a system, it transforms to an equal amount of some other form of energy. Let's unpack this. This is quite a complicated kettle of fish here. So we have 5 parts to a cylinder. We have the intake of fuel, then we have the compression of the fuel, then we have ignition of the fuel, then we have the power stroke where the gas that was ignited and exploded expands rapidly and you get that power stroke, and then we have the exhaust. So then we can talk about each one, A, B, C, D, or E. In the intake, a fuel-air mixture fills the cylinder as the piston moves down. B, in compression, the piston moves up and compresses the mixture adiabatically since no heat transfer occurs. And then you have C, the spark plug fires, ignites the mixture and raises its temperature. And then D, adiabatically, expansion pushes the piston downward, that's the power stroke. E, the burned gases are pushed out the exhaust valve and the cycle repeats. Figure 24.3, do work on a pump by pressing down on the piston and the air is warmed. When a gas is compressed or expanded so that no heat enters or leaves the system, the process is said to be adiabatic, Greek for impassible. Adiabatic changes of volume can be achieved by performing the process rapidly so that heat has little time to enter or leave, as with the bicycle pump in figure 24.3, or by thermally insulating a system from its surroundings with polystyrene foam, for example. Styrofoam, same. When work is done on a gas by adiabatically compressing it, the gas gains internal energy and becomes warmer. When a gas adiabatically expands, it does work on its surroundings and gives up internal energy and thus becomes cooler. Recall the activity in chapter 22 of blowing on your hand with puckered lips so your breath expands as it leaves your mouth. Repeated here in figure 24.5, your breath is considerably cooler than when you blow without expanding from your wide open mouth. Heat and temperature. Air temperatures may be changed by adding or subtracting heat, by changing the pressure of the air, or by both. Heat may be added by solar radiation, by long wave Earth radiation, by moisture condensation, or by contact with the warm ground. Heat may be subtracted by radiation in space, by evaporation of rain falling through dry air, or by contact with cold surfaces. There are many atmospheric processes, usually involving time scales of a day or less, in which the amount of heat added or subtracted is very small, small enough that the process is nearly adiabatic. In this case, an increase in pressure will cause an increase in temperature and vice versa. We then have the adiabatic form of the first law. Change in air temperature is proportional to pressure change. In figure 24.5, that's from the other slide, but let's review it. Blow warm air onto your hand from your wide open mouth. Now reduce the opening between your lips so that the air expands as you blow. Adiabatic expansion, the air is cooled. Pressure and temperature. Adiabatic processes in the atmosphere occur in large masses of air that have dimensions on the order of kilometers. We'll call these large masses air blobs. Due to their large size, mixing of different temperatures or pressures of air occurs only at their edges and doesn't appreciably alter the overall composition of the blobs. A blob behaves as if it were enclosed in a giant tissue-like garment bag. As a blob of air flows up the side of a mountain, its pressure lessens, allowing it to expand and cool. The reduced pressure results in reduced temperature, as shown in figure 24.6. Measurements show that the temperature of a blob of air drops by 10 degrees Celsius for every 1 kilometer increase in altitude, or for a decrease in pressure due to a 1 kilometer increase in altitude. Air flowing over tall mountains or rising in thunderstorms or cyclones may change elevation by several kilometers. So if a blob of dry air at ground level with a comfortable temperature of 25 degrees Celsius rose to 6 kilometers, its temperature would be a frigid negative 35 degrees Celsius. On the other hand, if air at a typical temperature of negative 25 degrees Celsius at an altitude of 6 kilometers descended to the ground, its temperature would be a roasting 40 degrees Celsius. When you're studying these blobs, make sure you remain cognizant about gas laws. PV over T equals PV over T. Pressure times volume divided by temperature equals pressure times volume divided by temperature. Now, Are you holding something constant or are you not holding something constant? As I decrease pressure, I decrease temperature. Remember, adiabatic means that there's no energy change. So if I have a giant blob, it's not losing energy, but as I decrease the pressure, what's happening to temperature? As I increase the volume of the blob, what's happening to the pressure, etc. So just make sure that you understand A, what does adiabatic mean, and B, be cognizant of your gas laws. Out in the American West, you have something called Chinooks, which are warm, dry winds, and they occur when high altitude air descends and is adiabatically warm. So you have a mountain, the weather's moving from west to east, and it loses its moisture on the westward side of the mountain. When it goes over the mountain, it's moving west to east. On the eastern side of the mountain, it's drier air, and it descends and it warms adiabatically, and that wind is called a Chinook wind. 24.8, figure 24a, the thunderhead is the result of the rapid adiabatic cooling of a rising mass of moist air. Its energy comes from condensation and freezing of water vapor. Remember, condensation is a heating, it's a warming thing, and so is freezing. Remember, the heat's going somewhere, and in this case, it's going into the development of the storm. 24.4, second and third laws of thermodynamics. If we place a hot brick next to a cold brick, heat flows from the hot brick to the cold brick until both bricks arrive at a common temperature, thermal equilibrium. No energy will be destroyed in accord with the first law of thermodynamics. But pretend the hot brick takes heat from the cold brick and becomes hotter. Would this violate the first law of thermodynamics? No, because energy is still conserved in the process. But it would violate the second law of thermodynamics. The second law of thermodynamics described the direction of heat flow in natural processes. The second law of thermodynamics states that heat will never of itself flow from a cold object to a hot object. Heat flows one way, from hot to cold. In winter, heat flows from inside a warm, heated home to the cold air outside. In summer, heat flows from the hot air outside into the home's cooler interior. Heat can be made to flow the other way, but only by imposing external efforts, as occurs with heat pumps that move heat from cooler outside air into a home's warmer interior, or air conditioners that remove heat from a cool interior to warmer air outside. Without external efforts, the direction of heat flow is from hot to cold. There is a huge amount of internal energy in the oceans, but all this energy cannot be used to light a single flashlight lamp without external efforts. Energy will not, of itself, flow from the lower temperature ocean to the higher temperature lamp filament. There is also a third law of thermodynamics, which restates what we've learned about the lowest limit of temperature. No system can reach absolute zero. As investigators attempt to reach this lowest temperature, it becomes more difficult to get closer to it. Physicists have been able to record temperatures that are less than a millionth of 1 Kelvin, but never as low as 0 Kelvin. What does the second law of thermodynamics state about heat flow? Heat engine mechanics. A heat engine is any device that changes internal energy into mechanical work. The basic idea behind a heat engine, whether a steam engine, internal combustion engine, or jet engine, is that mechanical work can be obtained only when heat flows from high temperature to low temperature. In every heat engine, only some of the heat can be transformed into work. In considering heat engines, we talk about reservoirs. We picture a high temperature reservoir as vast, something from which we can extract heat without cooling it down. Likewise, we picture a low temperature reservoir as something that can absorb heat without itself warming up. Heat flows out of a high temperature reservoir into the heat engine, and then into a low temperature reservoir as shown in figure 24.9. Every heat engine will, 1, increase its internal energy by absorbing heat from a reservoir of high temperature, 2, convert some of this energy into mechanical work, and 3, expel the remaining energy as heat to some lower temperature reservoir. In a gasoline engine, for example, 1, the burning fuel in the combustion chamber is the high temperature reservoir. 2, mechanical work is done on the piston, and 3, the expelled energy goes out as exhaust. According to the second law of thermodynamics, no heat engine can convert all heat input to mechanical energy output. Only some of the heat can be transformed into work, with the remainder expelled in the process. Applied to heat engines, the second law states that when work is done by a heat engine running between temperatures T hot and T cold, only some of the input heat at T hot can be converted to work, and the rest is expelled as heat at T cold. There is always heat exhaust, which may be desirable or undesirable. Hot steam expelled in a laundry on a cold winter day may be quite desirable, while the same steam on a hot summer day is something else. When expelled, heat is undesirable. We call it thermal pollution. Heat engine efficiency. Before the second law was understood, it was thought that a very low friction heat engine could convert nearly all the input energy to useful work, but not so. In 1824, the French engineer Charles Carnot carefully analyzed the cycles of compression and expansion in a heat engine and made a fundamental discovery. He showed that the upper fraction of heat that can be converted to useful work, even under ideal conditions, depends on the temperature difference between the hot reservoir and the cold sink. The Carnot efficiency, or ideal efficiency, of a heat engine is the ideal maximum percentage of input energy that the engine can convert to work. And this is the equation. Ideal efficiency equals T hot minus T cold divided by T hot. T hot is the temperature of the hot reservoir, and T cold is the temperature of the cold. Ideal efficiency depends only on the temperature difference between input and exhaust. Whenever ratios of temperature are involved, the absolute temperature scale must be used. And that should be obvious considering the denominator can't be zero. So that should make perfect sense. Fuel cells and electric vehicles. One of the attractions of fuel cells and of electric vehicles in general is that they are not heat engines. Their efficiencies are not limited by the Carnot cycle constraints of the second law, while the efficiency of an engine that combusts fuel will always be limited by the temperature difference between the cylinder and the exhaust. Fuel cells and batteries have no such thermal constraints. Fuel cells running on pure hydrogen can be as much as 80% efficient in converting chemical energy to electrical energy. Watch the growth of fuel cell technology and electric automobiles. Remember, a combustion engine in a car is about 25% efficiency on average, and really, in some cases, at best. So, T hot and T cold are expressed in kelvins. For example, when the hot reservoir in a steam turbine is 400 Kelvin, 127 degrees Celsius, and the sink is 300 Kelvin, or 27 degrees Celsius, the ideal efficiency is 400 minus 300, quantity divided by 400, which is 1/4. This means that even under ideal conditions, only 25% of the internal energy of the steam can be converted into work, while the remaining 75% is expelled as waste. This is why steam is superheated to high temperatures in steam engines and power plants. The higher the steam temperature driving a motor or turbo generator, the higher the efficiency of power production. Increasing operating temperature in the example to 600 Kelvin yields an efficiency of 600 minus 300 divided by 600 is 1/2, twice the efficiency at 4 Kelvin. And there is an example of a steam engine. Heat engine physics. We can see the role of temperature difference between heat reservoir and sink in the operation of a steam turbine engine in figure 2410. Steam from the boiler is the hot reservoir, while the sink is the exhaust region after the steam passes through the turbine. The hot steam exerts pressure and does work on the turbine blades when it pushes on their front sides. This is nice, but steam pressure is not confined to the front side of the blade. Steam pressure is also exerted on the back sides of the blades. Counter-effective and not so nice. A pressure difference across the blades is vital, for it causes the turbine to keep spinning, allowing it to do work. If pressures were the same on both the front and the back of the blades, no work would be done. How do you get a pressure difference? By condensing the steam, the pressure on the back sides is greatly reduced. We know that with confined steam, temperature and pressure go hand in hand. Increase temperature and you increase pressure, decrease temperature and you decrease pressure. So the pressure difference necessary for the operation of a heat engine is directly related to the temperature difference between the heat source and the exhaust. The greater the temperature difference, the greater the efficiency. Carnot's equation states the upper limit of efficiency for all heat engines. The higher the operating temperature compared with exhaust temperature of any heat engine, whether in an ordinary automobile, a nuclear-powered ship, or a jet aircraft, the higher the efficiency of that engine. In practice, friction is always present in all engines, and efficiency is always less than ideal. So whereas friction is solely responsible for the inefficiencies of many devices, in the case of heat engines, the overriding concept is the second law of thermodynamics. Only some of the heat input can be converted to work, even without friction. Figure 2411, try to push a heavy crate across a rough floor, and all your work will go into heating the floor and crate. Work against friction turns into disorganized energy. Figure 2412, the Trans-America Pyramid and some other buildings are heated by electric lighting, which is why the lights are on most of the time. Now, I'm not sure that this picture is actually current because lighting has changed and so is heating in the last 20 years. So this used to be absolutely quite true. This is in San Francisco. 24/6, order tends to disorder. The first law of thermodynamics states that energy can be neither created nor destroyed. The second law adds that whenever energy transforms, some of it degenerates into waste heat, unavailable to do work. Another way to say this is that organized, usable energy degenerates into disorganized, non-usable energy. The energy of gasoline is in an organized and usable form. When gasoline burns in an automobile engine, part of its energy does useful work, such as moving the pistons. Part of the energy heats the engine and surroundings, and part of the energy goes out the exhaust. Useful energy degenerates to non-useful forms and is unavailable for doing the same work again. Organized energy in the form of electricity that goes into electric lights in homes and office buildings degenerate to heat energy. This is a principal source of heating in many office buildings in moderate climates, such as the Trans-America Pyramid in San Francisco. All of the electric energy in the lamps, even the part that briefly exists in the form of light, turns into heat energy, which is used to warm the buildings. That explains why the lights are on most of the time. This energy is degenerated and has no further use. We see that the quality of energy is lowered with each transformation. Organized energy tends to disorganized forms. In this broader regard, the second law can be stated another way. Natural systems tend to proceed towards a state of greater disorder. Imagine that in a corner of a room sits a closed jar filled with argon gas atoms. When the lid is removed, the argon atoms move in haphazard directions, eventually mixing with the air molecules in the room. This is what we would expect. The system moves from a more ordered state, argon atoms concentrated in the jar, to a more disordered state, argon atoms spread evenly throughout the room. You would not expect the argon atoms to spontaneously order themselves back into the jar to return to the more ordered containment. This is because, compared with the immense number of ways the argon atoms can randomly move, the chance of them returning to such an ordered state is practically zero. Disordered energy can be changed to ordered energy only at the expense of work input. For example, plants can assemble sugar molecules from less organized carbon dioxide and water molecules only by using energy input from sunlight. But without some imposed work input, no increase in order occurs. In the broader sense, the message of the second law is that the tendency of the universe and all that is in it tends to disorder. What happens to the orderly state of any natural system? It tends to be disordered. Entropy 24/7. The idea of ordered energy tending to disordered energy is embodied in the concept of entropy. Entropy is the measure of the amount of disorder in a system. Disorder increases, entropy increases. According to the second law of thermodynamics, in the long run, the entropy of a system always increases for natural processes. Gas molecules escaping from a bottle move from a relatively orderly state to a disorderly state. Organized structures in time become disorganized messes. Things left to themselves run down, such as a house in figure 24:14. Whenever a physical system is allowed to distribute its energy freely, it always does so such that entropy increases, while the available energy of the system for doing work decreases. Entropy normally increases in physical systems. However, when there is work input, as in living organisms, entropy decreases. All living things, from bacteria to trees to human beings, extract energy from their surroundings and use it to increase their own organization. This order in life forms is maintained by increasing entropy elsewhere. So for the system, life forms plus their waste product, there is still a net increase in entropy. Energy must be transformed into the living system to support life. When it is not, the organism soon dies and tends toward disorder. The first law of thermodynamics is a universal law of nature for which no exceptions have been observed. The second law, however, is a probability statement. Disordered states are much more probable than ordered states. Given enough time, even the most improbable states may occur. Entropy may sometimes spontaneously decrease, although theoretically the haphazard motion of air molecules could momentarily become harmonious in a corner of the room, or a barrel full of pennies dumped on the floor could come up all heads, or a breeze might come into a messy room and make it organized. The odds of these things actually occurring are infinitesimally small. These situations are possible, but so highly improbable that they are never observed. The second law tells us the most probable course of events, not the only possible ones. The laws of thermodynamics are sometimes put this way: you can't win because you can't get any more energy out of a system than you put in. You can't break even because you can't get as much energy out as you put in. And you can't get out of the game. Entropy in the universe is always increasing. What always happens to the entropy of systems? Thermodynamics and thermal pollution. A modern electric power plant, though large and complex, can be approximated as a simple heat engine. The power plant uses heat from the burning of coal, oil, gas, or heat from nuclear fission to do work turning electric generators. In this process, it also produces waste heat as an inevitable consequence of the second law of thermodynamics. This waste heat is sometimes called thermal pollution because, like chemical waste, it pollutes the environment. Waste heat discharged into waterways can raise temperatures of aquatic environments enough to kill organisms and disrupt ecosystems. Waste heat discharged into the air can contribute to weather changes. Thermal pollution is unlike chemical pollution, since chemical pollution can be reduced by various methods. The only way to manage thermal pollution is to spread waste heat over areas large enough to absorb it without significantly increasing temperatures. Conservation and efficient technology are absolutely critical to the health of our planet. Critical thinking. Explain how the second law of thermodynamics tells us that it is impossible to produce usable energy with zero environmental impact.